Now, chapter 3 deals with radiative transfer, or as it is called, radiative transfer versus radiation in equilibrium. And hopefully we will see what I mean with that. Now, remember when we introduced the specific intensity, we said it was along some beam traveling in some direction n hat, okay? And then we said that the specific intensity is constant along this ray as long as there is no interaction with matter. Okay, but what if there is? And that's, you know, the case of analyzing radiative transfer deals with that. So how can we then set this up? Okay, then we're going to have some specific intensity going into some parts of this beam, okay? So we're going to cut out the little part here. And in this part now, along some delta S, where delta S now is a segment along this ray, okay? The radiation and matter can interact. And then we're interested in, okay, this is what goes in. How does this change? What is coming out? So then we will have that delta I nu, that is the change in the specific intensity, is just this one, okay? That depends on now the three different processes that we already said could happen. Remember, we had the emission of material, we had the absorption, and we also had scattering. Okay? So first we're going to analyze, okay, what energy is added to the beam? And then we're going to describe this with a coefficient. We're going to call it eta at a specific frequency nu. So that's going to describe how much energy, or specific intensity in this case, is added to the beam in this segment. And intuitively then, yeah, this is going to be proportional also to the length of the segment. Okay? We're not going to specify what this is now or where it comes from. Now, we can also then absorb material, as we discussed. Now, absorption, that's when you have radiation and then it's absorbed by the matter, for example, in a line transition or something like that, that we briefly mentioned last week. Okay? So then energy is removed, and that we're going to describe by another coefficient. We're going to call it alpha nu. Now, that alpha nu then will also be proportional to the length segment, intuitively, but it's actually also proportional to the intensity that is coming in at that point, which hopefully is also intuitive, because if you don't have any intensity coming in, of course, you can't absorb anything. There's nothing there. So that's going to be proportional to I nu at that point. Okay? So this will be our emission coefficient, and this will be our extinction or absorption coefficient. Extinction coefficient then normally deals with both absorption and scattering. That's, yeah, the difference. So the topic for calculating these, yeah, that is actually then in the coming chapters. Then we will see how different radiative processes that can be important in various astrophysical situations can give rise to various different expressions for this emission coefficients and this extinction coefficients. Now, in this chapter, we will always take them for, okay, we're going to say that we know what they are, and then we're going to analyze the nature of the transfer of radiation here in such situations where we know these. Okay? So first, we can just identify this. We can rewrite it to say that delta I nu divided by delta S is either nu minus a nu I nu. And if we put this now on differential form, which I did very mathematically tackle like this, okay? Then we have the basic equation of radiative transfer. Okay? So, importantly, along a ray in the n-hat direction. We're going to come to situations later where we're going to put this in some sort of geometric coordinate systems as well, right? Now, one we can call a vacuum solution. In a vacuum solution, we do not have any interaction with the matter, so these are just zero. That means that the I nu ds equals to 0 or I nu equals to constant. Yeah? We also looked at the equilibrium situation where we deduced from this that when this is constant and we do not have any transport of radiation, but we might not have vacuum, we might have a lot of interactions with the matter, but they equilibrize, and we have what we derived as Kirchhoff's law, which essentially is just this. Yeah? So again then, we have that the I nu ds equals to 0, or I nu equals a constant. However, here we define this constant to be the Planck function, B nu, as we defined. And we also know the specific now frequency dependence of B nu, and also its frequency integrated properties. So those are the things that we have already considered. Now, I wanted to mention one more thing about this. You can directly deduce from this equation that alpha nu must have units of 1 over length. Okay? You can just see this because this is just a differential, right? And you have I nu there, so this, in order to make sense, must have units 1 over length. But eta nu, as you can see, will not have the same units. So the extinction and the emission coefficients do not have the same units. So how can we then understand the emission coefficient? Well, we can use the, if you remember the definition of the intensity, right? We had essentially that the I nu was the energy, yeah, per some area, and then we had the solid angle dt d nu, okay? So now if we just derive this by ds, so we get ds here, you see that we get a volume element around the beam there, so that this is just then the dv, and then 1 over then dt d nu. So in that sense, you can see that either nu or the emission coefficient there can be thought of as a volume energy, the energy added to the radiation beam from the gas per unit volume. And then, of course, since we have our standard definition of intensity, it's also per unit time and frequency band, and into the solid angle here. Okay, as usual. But actually, it represents a sort of volume emissivity. How much energy is actually added to the radiation from the gas per unit volume, in that sense. So, some cases that we might be interested in looking at now is that, okay, what if we have something like this? This is something we will investigate here. This is supposed to be us viewing an astrophysical object, you know, likely from a great distance, so we can't resolve it so good, as we discussed last week, yeah? But then we're watching here. Now, that object is so thick that we can't see through it. We discussed already qualitatively the concept of being optically thick versus optically thin. Imagine the fog outside the window again. When it's very foggy, I can't see the wall there. Now, today, it's clear, I can. It's optically thin conditions, yeah? Now, for example, a star, our sun, the easiest, is very optically thick. We cannot see down to the center of the star, right? Which means that we can only see the surface layers to some depth here. And we will see that this is often on the order of optical depth unity, as we will define it. We call this typically some sort of semi-infinite medium or semi-infinite atmosphere. Because here, down here, if you were to calculate, then, in this case, the optical depth from the surface here all the way to, say, the center of the sun, this optical depth here would be so big that it essentially, for practical reasons, approaches infinity. Okay? So that's one situation that may be of interest. Another is that, well, perhaps you have a cloud, an astrophysical cloud, but that cloud is kind of transparent. So it's optically thin in that sense. You can actually see through it, but you can still see it glowing. Just that if you have some sort of semi-transparent here, you can sometimes see it glow, at least for us in the infrared here. And then we're sitting here watching that, and we can have an optically thin. Typically that's represented by an astrophysical nebula. If this is something like a star or, say, an optically thick accretion disk. You can't see through. This will be something like an astrophysical nebula. But you can also have that this nebula now might be what we call backlit. So you have an astrophysical nebula here. We're sitting here observing. And perhaps we're having another object back here, say a star, that's actually shining on this nebula, heating it up from behind. That is that you have an INU incoming here, which is very high or very low, depends on the situation in the cloud. Then the situation might change as compared to here when we do not have that with respect to what we see. These situations are the type of situations that we can and will analyze as we move forward with these descriptions in the course. Now, and which you also, yes?
The first word,
above star, accretion disk. Yes. Disk. All right, so now let's start to work with this. we had the equation here. Eta nu minus alpha nu I nu. We're going to rewrite this and use that to define some other useful quantities. We will divide through by alpha nu, the extinction coefficient, so that we get this expression instead, minus I nu, okay? And then we will use this to define two quantities. This indeed we will call d tau nu, and this we will call S nu, where you can see here that S nu is defined as eta nu divided by alpha nu. We call this the source function. And hopefully it will be clear after today why we call it the source function. Now, this other quantity indeed is d tau nu, defined as alpha nu ds, or if you do an integral here, you see that tau nu is the integral for nu ds. If you put limits here, you can put this between S1 to S2. Then this quantity, tau nu here, is indeed what we have qualitatively discussed as the optical depth. So it's this quantity that essentially determines then if an object is optically thick or optically thin. It's an integral quantity, which sometimes you can solve analytically and sometimes you cannot. All right. So hopefully those were straightforward definitions. Let's look at some simple examples of this. First, we're going to go here and we're going to say, okay, what if we have no emission, but we do have some extinction, which, as discussed, could be absorption of photons by the gas, or it could be scattering, depending on the situation. What happens to this equation then? Well, then we can just go back to that one, right? It's easiest. We can always choose if we want to work with this form or this form. They're identical, right? It's just more convenient sometimes there, it's sometimes more convenient there. In this case, it's obvious that it's more convenient there. Well, actually not. We could have just done it with that as well, because we could just set that the source function is 0 here. But anyway, let's work with that. Then we have that the I nu ds equals minus alpha nu I nu, okay? Like I said, actually, now we can use this form, the I nu, the tau nu equals minus I nu, all right? But that's actually not such a difficult differential equation to solve. So you can see we have the I nu divided by I nu equals to minus the tau nu. So if we solve this now, we just end up with the logarithm of I nu. So we're going to solve this, say, for here, where we have something coming in. We call it I nu 0. And then we're interested in the intensity here. Call it I nu m. Em, some length, yeah? We can define our optical depth scale so that tau nu 0 here is 0, and here we have some tau nu. Then if we solve this differential equation, hopefully this is something we remember from calculus 1, this will just be this and then minus tau nu, since this one was 0 per definition. We can always set the scale here. This is really delta tau nu, where delta tau is then the optical depth difference of this slab or atmosphere. Yeah? This we typically can write then as nu 0 e to the minus tau nu. So what does this tell us? Well, it tells us in this situation, when we have light shining, in this case from above, because that's how I defined it from the figure, then you see if we're standing here viewing that incoming radiation and it's only getting absorbed, okay, then we will see, depending on the optical depth here, this incoming intensity being exponentially attenuated. So again there, the simplest thing here, let's assume now that the building in the back there is radiating towards me, okay? Now, if there is no intervening emission in between me and that building, if the optical depth is low, 0, yeah? Then what will I see? Well, if tau nu in this is 0, then what I will see is just what was emitted, which is indeed the case here. But the higher the optical depth, say the optical depth is 10, that's just an arbitrary, then this will be exponentially attenuated by e to the minus 10. And e to the minus 10 is a very, very small number. Now, that's really optically thick, and I wouldn't see anything of the background source, I nu 0. Okay? This is precisely the reason why, for example, when we do astronomical observations in the ultraviolet or in the X-rays, we need to shoot up our telescopes in space. Why do we do that? Yes, atmosphere is very optically thick, but not in all wavelengths. In the X-ray and in the ultraviolet, in the optical, it's not very optically thick. That's why we can put the telescope here on the roof, right? And view it in the optical. Yeah? So the atmosphere is pretty transparent. So let's now assume this is the Earth atmosphere. It's pretty transparent, but in optical light. Yeah. Emergent. Yeah, that's just jargon. I could have chosen anything. But it's typically, we call this the emergent intensity because it's the intensity that emerges to your position where you're interested in. But perhaps for today, we can also call it I nu 1. Then that's the intensity at the position 1 here. Okay? Now, in the ultraviolet, when the sun's rays hit the Earth's atmosphere, they get absorbed. But since the Earth's atmosphere is kind of cool, we have discussed this, right? It doesn't emit very much in the ultraviolet itself. Yeah? This is good for our skin, that the Earth's atmosphere is not emitting in the ultraviolet. But perhaps then we would have adapted to be more tolerant to that. But that's a different story for another class. Now, the sun's rays are thus getting absorbed, but there is not much more emission added. That is, the emission here is very, very low. So we get essentially exponential attenuation. And now, since the extinction coefficient in the ultraviolet is very high, the optical depth becomes very high. And thus, none of the ultraviolet rays are penetrating to our location. Unless, for example, we have issues with those molecules that are actually absorbing then, ozone and other things. Yeah? Now, in the optical, this is not the case. The optical rays are not well absorbed by the Earth's atmosphere, so they can penetrate quite a lot. The atmosphere is optically thin, and therefore we see more or less what actually enters our atmosphere. Here, this one is roughly 0, so we see roughly I nu 0. Of course, there is some attenuation, and you have to correct for that when you do practical observations. But that's the way that you can think about this exponential decay. All right. Now, let's go to the general case. Where neither eta nu nor alpha nu is equal to 0. That is, we can also have addition to our beam. Okay? Then I'm going to write the equation in its other form, the I nu, the tau nu equals to S nu minus I nu. And then we're going to try to solve this. And we're going to do that with some assumptions now, that essentially we know the functional behavior of S nu. And then this week and next, we're going to discuss various assumed functions of this source function, and also what it might be under certain situations. So, if we assume that we know that, then we can see that this is a linear ODE. Okay? And that we also had in Calculus 1. Yes? We know how to solve this. We can solve it with an integrating factor. Yeah? In this case, we can just read off from the equation that the integrating factor will be tau nu there. Okay, so let's do this. If we remember, this is the I nu, the tau nu. Then we multiply by our integrating factor e to the tau nu. So, of course, the integrating factor is e to that variable. Yeah? That's equal to e to the tau nu, S nu minus R nu, right? And the trick here is, of course, to realize that if you have now the tau nu of that whole thing, I nu e to the tau nu, yeah, and you just do that, that should be the I nu, the tau nu e to the tau nu plus I nu e to the tau nu. And then we can do identification if we did our integrating factor correctly. Indeed, we can. We see this term. We see this term. So we can write this as the tau nu of I nu e to the tau nu equals to e to the tau nu S nu. Okay? And now we can try to solve this. So then, if you again, let's put the little geometry sketch here to the left. We're going to have something like this again. And then we have some slab here. Yeah? And we're looking at rays along this n hat direction there. So this is RDS. Yeah? And then we have some incoming radiation here. Let's call it again I nu 0. And we're interested in now what comes out on this side, which is, so to say, the reason why I call this I nu 1 or I nu emergent. Yeah? Again, we can just put our definition of our optical depth scale so that tau nu 0 equals to 0, and the tau nu here will just be tau nu, representing the optical depth of this slab then. Okay? And then we can see what will be here is I nu emergent, e to the tau nu, right, minus I nu 0, the incoming there, e to the tau nu 0, and then equal to, and here now, as you can see, the solution will depend on the functional behavior of S nu, the source function. Yeah? If S nu is an explicit or implicit function of optical depth, then you will have to keep the integral here. And we will look at such examples later. Yeah? Now, sometimes, I already mentioned this, things can get even more complicated if S nu is not just a function of the optical depth, but also on the intensity itself, or the mean intensity that we defined, A nu. Then, of course, you can't really solve this directly. And that's where we came to these type of iterative solutions that we qualitatively discussed last week. Huh? That's typically the case when we have scattering, not pure absorption, just to give you that idea already now. We will discuss that briefly in this course, and for those of you in the master's program, you will discuss it more in the spring when you take stellar atmospheres and winds there. Now, for now, we're going to assume, okay, let's assume that S nu is a constant. Okay? That doesn't depend on tau nu. Yeah? Then we get S nu e to the tau nu minus e to the tau nu 0. Okay? However, we already said that we put our optical depth scale such that tau nu 0 equals to 0, right? So if we do this, then we can directly see that we have I nu emergent minus I nu 0, this will be 1, equals to S nu e to the tau nu minus 1. Or, as we normally often put this equation, E nu emergent, I have forgotten an e to the tau nu here, you should have notified me of that, equals I nu 0 e to the minus tau nu plus S nu 1 minus e to the minus tau nu. Now, this is a solution to the transfer equation that you will encounter if you take astronomy classes in many of your classes, because it's the simplest case that can be solved analytically, and it can be used to discuss a lot of insights. Typically, you see it as the solution of the RT radiative transfer equation through a homogeneous slab. Okay? Hopefully slab is obvious from the geometry, sort of say simplified geometry that I sketched here. So to say you have rays going in that direction, yeah, and slab material there. Homogeneous, that's essentially because if the slab is homogeneous, then it turns out that the source function is constant. So then this is valid. Now, what do I mean by a homogeneous slab? Now, typically, a homogeneous slab means that the density and the temperature of the slab are constant. Okay? Now, we will discuss how to calculate source functions later, but if these conditions are true, yeah, then typically this is also a constant. Okay, which is why we look at this as the solution through a homogeneous slab. Okay, okay. We'll start again. We'll start again. We'll start again. Where were we? Well, we were at our general solution for the radiation transport equation through a homogeneous slab, where we're interested in, I call this I nu emergent, the emergent intensity after whatever radiation has gone into the slab has interacted with the slab, which here has an optical depth of tau nu, and we assume that it is homogeneous, or technically that the source function is constant. And then we had our solution. Now, the first thing we want to know is to get some reality check on this, right? So if we remember our definitions, the optical depth, right? That was just the integral. In this case, it would be, if we call this from, say, S0 to S1, from S0 to S1 of alpha nu ds, right? So we can directly see that, okay, we have also S nu is just eta nu over alpha nu, so that's a constant. So if we can also assume, which we sometimes can and we sometimes cannot, that alpha nu is constant in space, then of course this we can say is just alpha nu S1 minus S0, but then we might as well just call this alpha nu L, where L then is the length of our slab. Call it L. This is a slab of length L then, okay? Then we can write this, and we will use this, for example, when we try to estimate later in one of the applications, the density at the gaseous ionizing nebula from its emission. What did I more want to say? Right. First thing that we might want to do is to check, okay, what if now we had our previous case where we had the absorbing atmosphere but with no emission, right? Then we said eta nu was 0, yeah? But if eta nu is 0, then S nu would also be 0. The source function would be 0. What do we have then? Well, then we indeed have that the emergent then is I nu 0 e to the minus tau nu. So that's a good sanity check because it's the same expression as we had when we discussed the absorption of incoming solar radiation through the Earth's atmosphere in the ultraviolet versus the optical. So we know that we preserve our previous cases. Similarly, we should know that, okay, if S nu, if eta nu is 0, but if alpha nu is also 0, then S nu is of course ill-defined. Yeah? But you can rewrite it, of course, in the other form, and then if alpha nu is 0, you can see here directly that tau nu will also be 0. So if tau nu is 0 and alpha and S nu is 0, you see that you indeed have I nu m equals to I nu 0. This is if there is no source, but there's also no optical depth. And then we just have a transparent slab, nothing is happening, there is no interaction, and we just see whatever intensity came in. So that's also another good sanity check that we are okay with our basic equation there. So now we're going to take an example, two different examples. We're going to look at first a case where tau nu is much, much greater than 1. We have already discussed. What do you think? What is this? The slab is very, what do we call it? Optically thick, indeed. And then we're going to look at the case where the slab is not completely transparent, but almost. Yeah? Then 0 is actually smaller than tau nu, because if it's per definition 0, then this is just it. However, it is much, much smaller than 1. This is typically then what we call optically thin conditions. Yeah? It's not fully transparent, but almost. So, first case, if it is very optically thick, what do we think will happen? Well, we already know that it's tough to compete with an exponential. So, we can just neglect this here, and we can just neglect this there. And we can directly just read off our basic equation that our E mu will be roughly S nu. Hence the name. Source function. What does this physically react to? What I have just done here, if you're wondering, is that I neglected e to the minus tau nu. If tau nu is much, much greater than 1. Like I said, if you compete to an exponential, you will always lose. So this one will lose out, and this will go to 0. Similarly here, this will just go to 0, so you're left with only S nu. Physically, this means that you have something that is incoming, right? You have your slab here, and you're interested in what emerges here. This is where you are watching, yeah? What emerges down here. But, of course, if this is very optically thick, all the incoming light here is just absorbed. And what is left? Well, in the previous case where we didn't have any emission, then what was left was nothing. Well, the ultraviolet was absorbed. But here, we do have a source. So, what is left, as you can see from the equation, is just that you see S nu. Whatever that S nu might be, that's what you will see. And that's indeed why we call it the source function. You see only the source. there are plenty of analogies to this. You can even make an analogy that if I have a light source in, well, let's say the classroom we're on Friday, 60 there, right? Yeah, and I put that light source and I just look at that, stare at it now. Do I see anything? No. I will not see that light source. Why will I not see that light source? Yes. The wall is optically thick. Yeah. So I only see the source. And the source in this case is the wall. Okay? It's not a perfect analogy because the wall is actually a solid. But imagine now that we have the same situation, but there was only gas. Yeah? And then I put the source there, but the gas in between the source in the room and me here was so optically thick so I couldn't see the background source. I would only see then the intervening source, the source function here, whatever that might be. Okay? Now, we're going to look at the other example, and then we're going to use our Taylor expansion again because we had those conditions. Remember that the one Taylor expansion we wanted to know from this course was this one, yeah? So in this case, of course, it's just e to the minus tau nu is approximately 1 minus tau nu, yeah? And we have up here that I erased the equation. Lovely. Let's see if we remember it. Hopefully we do. Okay. So then we have I nu emergent equals I nu 0, 1 minus tau nu, plus S nu, 1 minus tau nu. So this is just then 0, 1 minus e to minus tau nu, plus S nu tau nu. No, why did I say that? This is not like this. Okay, we can just write this then in this convenient form that I nu emergent is I nu 0 plus tau nu, and then we see S nu minus I nu 0. Okay, so now it's getting interesting. Because here you can have different situations, right? First, of course, you see that if the optical depth is strictly 0, you have nothing here, so it's just the incoming intensity, which makes sense, which has to be, otherwise we did something wrong. Now, however, if that is a small quantity, but non-zero, then you can see that if now S nu is greater than I nu 0, okay, then I nu emergent is actually greater than I nu 0. We have had addition to the beam. Okay? On the other hand, if S nu is smaller than I nu 0, then we have that I nu emergent is also smaller than I nu 0. if S nu equals to I nu 0, then as you can see, then indeed again I nu emission will just be the intermediate, because yeah, then we might have a source and emission, but nothing happened because our source is the same. It's a background source. So in part of later during the course, we will use this in our application 8.3 in the lecture book to explain why certain astrophysical objects have emission line and certain have absorption lines, as we qualitatively have discussed. And we can already now do some sort of qualitative discussion of this, actually. It does require us to know a little bit about what the source function is and the incoming intensity. But since we have already discussed equilibrium radiation, then we know that for such equilibrium radiation, the intensity is the Planck function, right? And it turns out that locally, this is also sometimes, quite often, not such a bad approximation. And we will come to also then with some more quantitative derivations of it, why this is actually the case. But let's now, just for now, assume that the incoming intensity is indeed the Planck function, okay? At some certain temperature then, at some frequency, yeah, we know the Planck function, yeah? It's 2h nu cubed c squared, 1 e to the h nu kt minus 1, right? So we have that at some frequency, so let's just call that at some temperature T0, okay? And now let's say that this source function is also the Planck function, but that can potentially be at the same frequency, but at some other temperature, T1, okay? That's just the same functional form at the same frequency, you just insert a different temperature in the Planck function, right? Okay? Now, remember when we sketched the Planck function during the last class, or 2 classes ago, for different temperatures, what did we learn? Well, we learned at a given frequency or at a given wavelength, a higher temperature of the Planck function meant that the value was higher. Indeed, always that case. So what we know is that if T1 is greater than T0, then B nu of T1 is also greater than B nu of T0, and of course vice versa. So let's use this now with our optically thin approximation there. Yeah? In this case. Then, well, what can we say? Okay, let's assume we have our slab here now. We have our observer here. And then we have something which is emitting there with some incoming intensity there, right? Okay? Now, that incoming intensity is just given by the Planck function of some temperature, and this one is just, well, which one did I call T1? T0, yeah. And I call this one B nu of T1, okay? And we're interested, what do we see from this? Well, as you can see, if this gas cloud here has a higher temperature than the source, whatever that source here is, then we will see that the emergent intensity we see is higher than the background source. Okay? So now assume that we don't have any background source. Then this is 0, right? Then this is always emergent intensity. And this is indeed when you have like a cool or a 0 background source that is shining through a nebula, you get emission. Or if you do this for a line, you get emission lines. Vice versa, if you have a hot background source, which is shining through a cool nebula, what do you get then? Absorption line, because the emergent intensity is lower than I knew. So you have a hot background source shining through the nebula, then you get absorption lines, okay? So that's the basics for the figure, which I actually think I also included in the lecture book that you also saw for those of you who took inledning tot det sterrekunde, and then you have your nebula there, and then you call it reflection, or you call it there. But this is actually the reason why you could say that, okay, this is an emission reflection nebula, this is an absorption nebula. This is the physical reason why that is. And actually, we can generalize it even further to have the first qualitative understanding why the lines that we saw from the stellar spectra last week, remember that we looked at it and we could deduce from Wien's displacement roughly what the temperatures of the star was, because we approximated with a black body. Well, you say, this doesn't really look like a perfect black body. Of course, it's not. But we also had these sharp features. That's the spectral lines, right? But if you notice from these figures, they were typically always in absorption. It's not always the case, but for most cases, they're in absorption. Okay? Now, we can actually understand this, and we can use this even to qualitatively understand that. Because how can you view a stellar atmosphere in that sense, in this simplified sense? Yeah? Well, now I'm going to put ourselves here, right? Well, okay, let's put ourselves here. And then we're viewing the sun here. Now, what are we actually viewing then? Well, we're viewing a very hot, we know it's very hot inside the sun, okay? We might not yet know why it is, but we know it's extremely hot inside the sun, right? And then it shines through, and we know that its atmosphere, we estimated this from Wien's displacement law, is on the order of 6,000 Kelvin, 5,780, right? On the order of that, okay? So if we just now view this little atmosphere of the sun as one of these layers, and then just calculate, we treat it as a homogeneous slab here, okay? And then we just say, okay, we have a hot source which is shining through the atmosphere with the radiation emergent here. Then again, we have something which has a very hot background shining through an atmosphere which is cooler, which, as we saw here, again leads to absorption conditions. Now, of course, what we will see in both this course and in later courses is that, well, this is a qualitative picture of why lines are in absorption. But actually, the temperature is, of course, not constant. It must increase from this to this. So what we have done now is that we've just set it constant here, and then it just increases magically there. But it's, of course, a gradient all the way here. And when it's a gradient all the way here, we come to the other problem in our transfer equation, because remember when we set up also along the ray. Yeah? We set up the transfer equation as this differential equation, right? Equal to e to the tau nu s nu, or d there and d tau. Yeah? But if this now is no longer constant as we assumed, then we can't solve the integral in the same way. We have to account for that dependence. And again, in practical research applications nowadays, typically this is not a known function, so you will have to do it by some numerical techniques. But what we will also do is that we will assume some functional dependence of this with tau, yeah? For example, a linear, which is not such a bad approximation, actually. That's linearly dependent on tau, and then we can actually solve it again analytically and deduce various properties. For example, we'll learn about the phenomena of limb-darkening from that solution. Okay? So that's one complication that we need to deal with moving forward from here now. Another complication is, of course, okay, but now we have just looked at one ray, but typically when we discussed, remember we had the surface and then we needed to look at all the rays that were outwards if we wanted something like flux. So, of course, when you have a sphere, you can have rays coming from there or there or there, yeah? So that's another complication, and that comes into a sort of a conceptual as well as technical, quite difficult part of this to get a grasp on, which is how do we now handle it when we just not have like a simple slab solution like here, where we can understand the solutions as going through, yeah, but we also need to put some geometry on the transfer equation. All right, so the last time we analyzed the radiative transfer equation, looking at some simple solutions of it, specifically the homogeneous slab and what that contained, and how we also could connect that to various, on the basic level, various astrophysical contexts and examples, okay? Now, today, we're going to dig deeper into some fundamentals of the radiative transfer equations. So today is going to be quite technical, I guess, to some extent. But I do wish to introduce you to some more of the subtleties, we can call it, of the radiative transfer equation. So at least you have seen it once, and you know how to do those parts, so that, I don't know, if you in the future something come across and it's just thrown up there in some course, you know that, okay, but this is the transport equation in this form, in that form, etc. And that you also, I don't know, if you want to do something like analyze the light curve of a transit light curve from an exoplanet, and you need to account for limb darkening then in order to get the parameters out of it. You know, where does this limb darkening actually come from, really? And also, I just find, I've already talked about, you know, we see roughly until optical depth unity, we define the photosphere at some sort of optical depth average 2/3. I mean, where do these things come from? And hopefully that will be clear after today's class, where we will dig into this. So we start again with the transport equation now along a given ray. Again, we had the ray, it was in some n hat, we had some path length delta s here. Okay, now I'm going to do a little bit of a Taylor expansion here of the intensity, moving from that to this. and actually also then take into account that it takes some time. Speed of light is fast, but it's not infinite fast, right? So you have to take the time shift also technically into account there. And then, of course, if we keep the first order terms, this is just the I nu ds delta s plus the I nu dt delta t. But then we can just see this, we can rearrange, we take down the delta s from that, we move over this, and we see that we had essentially how we defined the transport equation before, so that we can write it, in this case, in this form, which is then the I nu ds plus 1 over c the I nu dt, where of course used here that delta t over delta s is just 1 over c, speed of light c. And then we add the sources and the sinks on the right-hand side again. And then we can see that now we have obtained a different form. It's actually a partial differential equation now when we keep the time derivative into it. Yeah? So before we start to move on with what is this ds really, I wanted to make one remark here, and that is, you see we have the nu here. So essentially, what I've done here is that I've assumed that the frequency nu does not change, right? Now, the thing is that at least when we have moving media, then that's no longer strictly true, because then we're subject to the Doppler shift. Yeah? We will come back to this Doppler shift later during the course when we discuss line profiles and line broadening in more detail. But it's essentially that when you have a source, it's the same as the traditional ambulance type of effect, right? That when you have in this case, I am, say, an atom within the moving astrophysical gas, and then I have some light coming at me from this direction. And then, of course, if I'm moving in this direction, the photons that reach me, I will see them because of the velocity in the line of sight as redshifted. If I move towards them, I will see them as blue shifted. Yeah? And that's the Doppler shift. So technically, when we have that, we have to also then take that into account. And essentially, we have two options for it. So we can add it to the material interaction terms, the emission and extinction coefficients, okay? So we say that, okay, we account for the Doppler shifts when we actually calculate these terms. That's not the subject for this chapter, but for later. So that's one way of doing it. The other way of doing it is to say, okay, we're going to transform ourselves into a frame that is actually co-moving with the fluid or with the gas. We call that the co-moving frame. It's equivalent to the Lagrangian frame. Yeah? So if you do that and you transform it to the co-moving frame, then you, then you unfortunately also then have to account for the frequency derivative here in your side. So you have to add that term to this. But this is for the co-moving frame. And for the purposes of this course, I just wanted to give you that in case you encounter that. For example, if you ever move on and do research with me or my group, then you will certainly encounter this. But here we're going to just assume that we do not have any velocity for the purpose of understanding the basic radiative transfer equation. It makes life easier for us. So then we don't have to account for any possible frequency shifts. Now, okay, and we also see, of course, from this exploration that the equation of transfer is a linear equation. We have only accounted for the linear terms here. So the question now becomes, what is this ds here then? Okay. So first we can look at, okay, we're going to put some coordinates to this. So we're going to look at it from a Cartesian coordinate system. And what is then ddx? Well, it's do I do this in the easy as well? dx, ds, dds, no, ddx plus dy, ds, dy plus dc, ds, ddc, okay? However, here you can of course see that this is just nx, this is just ny, this is just nc, where n is our unit vector that we have introduced before. And here you see your gradient Doppler vector, so you can actually write this as n hat, scalar product, dot product with the gradient operator. Yeah? So, then we can reformulate this in the sort of neat way, di nu dt plus n hat gradient of I nu, the mu I nu nu. So there we have that form of the radiative transfer equation. Okay, now let's assume now again that we have a 1D medium where we have variations only along, in a Cartesian sense, the vertical, so along the c direction, and we can assume that it's stationary, steady state, so d dt is 0, okay? Then we already have calculated, we know that the nc component is cosine of theta, which we typically call by mu, right? So we can just write that down. It's mu di nu d theta equals either nu or nu I nu, okay? And this is now the radiative transfer equation for a 1D stationary Cartesian situation with variations then along the c-axis. Oh, sorry. I'm going to take this first. All right. So, where we at? Mu di nu dc, either nu alpha nu I nu. Okay, we're going to keep that in a little box here. And let's discuss it a little bit. So the first thing is that this is no longer now along a ray, right? This is defined along the vertical c. Okay, along some sort of vertical axis, c here. Okay, where, you know, along the line, of course, we would have that this is true. Okay. Now, if you look at the rays here now, this is some sort of n hat then, yeah? And this is our theta angle, okay? And then it's traveling through the media there in the direction specified by n hat, mu here. Now, what you can see and what is so nice with this is, of course, that once you have traversed a certain way within your media, and you come up here, you can just look a vertical there, then along this ray, and you put a theta 1 there, you put the theta 2 there, you see that theta 1 equals to theta 2. There is no variation of the theta angle here. There is no variation of mu which makes life easy. Now, of course, there is a certain problem here. And that is that a lot of astrophysical objects we're interested, I mean, they're not Cartesian like that, they're more spheres, with the most obvious example perhaps being a star, as I heard from the audience, whispering very slow. Anyways, a star is a sphere, you know? It's not a Cartesian object here. The Earth is also a sphere, by the way. Yeah? If we want to think about the atmosphere of the Earth. Now, what happens when we have a sphere here? Okay, let's try to draw this. This is going to be horrible, and I apologize in advance, but we're going to try. Oh, you see? There would be something like the center of the sphere, right? Okay. And we have some second layer here somewhere. Okay. So now we have a sphere, an extended sphere. And if we now take a ray through this sphere, let's say we're sitting somewhere there, so we want a ray along our direction. Okay. Then, of course, yeah, we're going to do a radius here. It will be our R1. Okay. Then we have our theta 1 here. Okay. But then if we're going to look at, say, let's say that this is the surface of that object. And we're going to try to do the same thing here, right? Because now the variation is along these radial shells. Then theta 2, then hopefully my drawing was not so bad that you cannot tell that theta 2 is actually smaller than theta 1. So when we have a ray through this configuration, the theta angle changes. The mu angle changes. Okay? And that is not very pleasant at all, because it means that when we now evaluate DDS, we're going to have to go from just considering n hat times the gradient to also consider the change in the unit vectors. Okay? Now in full 3D, where you have 2, you have theta and phi, this becomes a complete mess, because of course if you think about the spherical coordinate system, the standard notation for the polar and azimuthal angles are also theta and phi. Yeah? So in the course book, for example, then I denote them by big theta and big phi, and the radiation angles as small theta and small phi. I cannot draw that. I'm not even going to attempt. It's just going to be a complete mess. And actually, the full derivation here in the 3D coordinate system is, well, it's vector calculus. It's vector analysis, doable, straightforward, but quite intricate. If you want to see it, for example, the authoritative textbook on this subject of stellar atmospheres by Hubine and Mielas give this the full expressions. What we're going to do here today, though, is that, okay, let's assume again that we have our 1D media, time independent. We have variation along only the r-axis. We call that the spherically symmetric media. And then we can work this out, hopefully. Then can see that the DDS is going to be the RDS DDR plus d theta ds d theta in this case. Now, the RDS, we can just read off actually from the geometry of the situation. That is just going to be, again, cosine of theta equals to mu. So there we have that. The question is, what do we do with this? Well, we can realize that the constant along this ray here is what we typically call the impact parameter, and that's sine theta times r. You can try to convince yourself that this is the preserved quantity here. Now, say that this is a constant now, and then we can take the PDS on that one, okay? So that's just then dr ds sine theta plus r cos theta d theta ds, and that will be 0. But this one we already know is cos theta, so you can just cancel these out, and you get the theta ds equals to minus sine theta divided by r. So there is your variation now that you need to apply in your spherically symmetric transfer equation. So, so that was the 1D Cartesian case, and then we had said that the SDR equals minus sine theta divided by r, I think. Yeah, so we're going to do the 1D spherical case then, which will then be mu, the I nu, the r, plus 1 minus mu squared divided by r, the I nu, the mu equals eta nu, alpha nu, I nu, where I've again, of course, used here. This was, if you recall, the equation was actually the I nu, the theta, right? But of course, I've just used that mu equals cos theta, and the theta, the mu, the theta, the mu, the theta equals minus sine theta, to just change the variable into mu, which is typically what is done. So you can see that in even in 1D Cartesian, no, in 1D spherically symmetric media, this is a partial differential equation. We have a variation in mu that we need to take into account, and it's actually quite a bit tricky. It is what you need to apply in systems like the solar corona. If you have a stellar wind outflow from a star, or even if you have like an atmosphere around a very large supergiant star, then this is typically the equation that you need to apply. However, for many situations, there is an approximation we can use here, which is very useful. So now we're again gonna do the spherical configuration here. You see this? But now we're gonna say that, okay, the atmosphere is very thin as compared to the underlying radius, like this. Okay? And now if we draw our n hat vector here, and then we're only interested in this little layer, okay? And now we're going to see if we can do this. Probably not again. probably you can draw it better, then you see that this angle here, nu1, you have to draw this yourself to get an appreciation, and nu2, because this is such a thin, nu1 equals to nu2, okay? Then we can neglect the variation in theta or in mu, because the atmosphere here, or the media here, is so thin as compared to the complete radius of the object. And then again, okay, we neglect this variation then. We set this to 0, d mu, then we see, what do we get then? Well, we get mu, the I, the R, equals eta nu. Okay. Now, what do we see by this equation? Well, let's compare it to the Cartesian case that we had above. Are there any differences here? Yes. Exactly. So, from the audience, we had that instead of differentiating in the C direction, you just differentiate in the R direction. Completely correct. And that's the only difference. So, if we just replace the initial C axis by the R axis, or vice versa, we can interpret the C axis there as the R axis in our spherical system whenever we can neglect this mu angle. Now, you can even, from here, you see that the condition that has to be fulfilled for this is that delta R has to be much, much smaller than R, where R is the characteristic radius here, until the start, say, of your atmosphere, we can call this. And then this is delta R then. If this is not the case, we go back to the first case, we have the variation. However, now you can think about a few examples. The atmosphere of the Earth is not so high as compared to the radius down to the center of the Earth. The photosphere of a star, or the atmosphere of a star, is actually typically much, much thinner than the underlying radius of the star. Now, in these type of situations, this is controlled typically what we call the scale height. And that's then governed by that we think that we typically assume that an atmosphere is in what we call hydrostatic equilibrium. We have sort of alluded to that a little bit in our basic discussions here. It essentially means that the downward force of gravity is balanced by an upward pressure gradient, which for the very massive stars that I work with can actually be dominated by the radiation pressure gradient. Here on the Earth, it's the gas pressure gradient. It prevents the air from falling from the ceiling here to the floor, which, you know, wouldn't be so pleasant for us, I guess. But we build up a pressure gradient. The atmosphere. Now, the typical height of that is the calculation done in other courses here. Yeah? But you can have, okay, you can do a calculation. There is an exercise for you in the booklet of this where you can just estimate it. That this is related to the so-called scale height. The scale height is typically the height over which, say, the pressure, the density in your atmosphere changes by a factor of E. And that sets a characteristic scale there. And then you can compare this to the characteristic scale of your complete object, be it the Earth, be it the star, or be it some other object, and see whenever this is fulfilled and whenever it is not. Now, this is called the plane parallel approximation. And it's indeed so we're going to now use this, and I'm going to set it up. And then after a break, we're going to do some classical solutions to this. Now, okay. So we had this, and we're going to call it the z-axis now. But we could as well, if we allude to the plane parallel approximation, call it the r-axis, right? And then, okay, we have our plane parallel layers, right? We have the z-axis, yeah? Then it's custom, so to say, to actually define now an optical depth scale, but in the other direction. So going from here inward in the object, okay? So that would be your tau nu C scale, where typically you see that at the surface of this object you would have optical depth equals to 0 in the absence of external radiation. Yeah? And it increases inwards. So in that sense, you would define the tau nu C as minus alpha nu dc in the other direction, or that tau nu C from some C1 to some C2 is just alpha nu dc here. So if you plug this in now, you of course, you will see that this nu C, the tau nu C is going to be I nu minus S nu, where S nu is our source function again. Now, again, it is important that this now is the optical depth not along the ray. Yeah? It is the optical depth along the vertical here and directed in the other way than the z-axis. And of course, we see that the right-hand side here have flipped signs because of this. Yes, please. Sorry? Next to the left arrow, here. Ah, yeah, this is just me doing this. No, sorry. This is tau nu C. All right, so it is the optical depth axis going here, and this should actually be a vertical line. It's not really vertical. I put a little tilt on it. I shouldn't have done that. Yeah, just down there. All right, so now we have what is actually classically the radiative transfer equation analyzed in a 1D plane parallel medium. Okay? We can see that actually we can solve this in a way that is very similar to what we did for the homogeneous slab. It's a linear OD, and we can apply an integrating factor and then solve it. So we're going to look on that for specific media after a short break now, and get to some hopefully interesting solutions which will clarify concepts like limb-darkening, optical depth, etc. Equation for one-dimensional plane parallel systems. So we can see that this again is a linear ODE now, with a fixed optical depth scale along the z-axis as discussed. And of course, we can solve this then with the same sort of technique as we did the last time for the homogeneous slab. Only here we have to apply a different integrating factor. Hopefully it should be intuitive, Previously we had tau nu, right? That was along the ray. So now we have tau nu theta, but we have to divide it by mu. We also have to put a minus sign because we have switched the signs on that because of the axis directions. Okay. And if we apply this, we can solve it. Yeah. But we did it already for the homogeneous slab. So now I'm not going to do it again. Now I'm just going to write down the solution, and we're going to discuss what that solution means. I'm going to try to interpret it a little bit to that. You can do the solution. It involves a little bit of algebra. It's actually an exercise in the booklet, and there's even for a solution for you provided by the TAs in the corresponding booklet for that, right? So it is there. I'm going to write down what we now call the formal solution of this equation, which is now I nu of tau nu 1 in the c direction, it's a function of mu, equals to I nu tau nu 2 in the c direction, it's a function of mu, plus e to the minus tau nu 2 minus tau nu 1 c direction, where this is of course tilted with the mu, divided by the mu. Then we have to add the source function part to this, and we have not assumed now that this source function is constant as we did for the homogeneous slab. So then we're going to have to keep it inside the integral. I'm going to put it as t nu e to the minus t minus tau nu to c divided by mu d t nu divided by mu. So this is a very nice expression. It looks cumbersome. Let's see if we can interpret it a little bit. Huh? Here we have it. So first, formal solution. That is because the work is actually not done. We've just written down the solution, but we haven't solved the integral, right? Now, it is only in special cases, like previously in the homogeneous slab, we assumed that this source function here was constant. So then we could just plug it out, and then we can solve it directly, right? There are other instances, like the one we're going to discuss later in a few minutes, where we can assume some sort of dependence, and then also solve it analytically. Now, today, most of practical research applications as well, they solve it numerically. So then you have to obtain your expressions for the source functions from your medium, expressions for your optical depth scale, and then solve this equation numerically with some sort of technique. Now, what does this equation mean? Well, first, let's see, we have the media here, right, with our plane parallel layers, and say we have some sort of intensity I nu there of tau nu 2, and along some angle mu, right, where mu is defined by this theta angle here. And then we have another position there, up there, which then is I nu 1 and mu. Okay, so then imagine here was our source in this case, if we make the analogy to what we had before. And then we're interested in how does the specific intensity along the ray here change as we come up here. Okay, that's essentially what it says. We have this solution here, which is this incoming, or the meridians, and then this is modified by this. And the first term here is familiar to us from our previous class, from our previous lecture. It's just this exponential attenuation law of the source, the extinction, the absorption part, right? Now here you see that this is just governed then by the difference in delta tau nu theta, that's this. But then it's tilted by mu because, of course, the path length is a little bit longer here. Yeah? So that's just that part. And then it's exponentially attenuated. And then we have the source. And that source function now, yeah, where t here is just an integration dummy variable. It's just to not confuse it with all the taus that we have moving around, right? Now, the source here is not just from the background or anything. The source here now, technically, is added at each of these small points along the ray until we reach the final position. Okay? Now, if you add some beam here, a source, then of course that has to also travel all the way up there. This one is added there, it has to travel all the way up there, etc., etc. So there is your source, but then that source is attenuated with the light that is the difference between the I nu 2 and the actual position. Okay? So from that until the position where we want to integrate to. Okay? And then, of course, again, we have the tilt in mu, and we have the tilt in that. So that then, when you sum this all up, it becomes an integral. You know, integrals in this context are just sums. You sum up all the contributions, they're all exponentially attenuated, and then you get the final answer up here, which then involves solving this integral. So that's essentially what the radiative transfer equation and the transport of light there means. Now, let's look at this for some special, hopefully interesting, at least they should be somewhat relevant examples. Now, let's say that we are up here, very far away. Our plane parallel atmosphere here, all right. And t-axis somewhere around there. And then the tau nu c-axis going in this direction here. Now, at the surface, at the end of the object, we have free streaming in vacuum until the light reaches us, very, very far away. So here, tau nu of c, can set this to 0, all right? Now, this object is very, very thick. It's optically thick in this case. Think about a star or an optically thick accretion disk or something like that. So down here, when we move, then actually tau nu of c, we can take it as going to infinity. This is called the semi-infinite medium or atmosphere, since that is where it is classically derived from for in the context. Now, we are then interested in obtaining the intensity here at an optical depth 0 and at the angles mu. And that we call then the emergent intensity. We could also, and that's technically what one needs to do when one, for example, do models of these type of systems, we could be interested in the radiation field inside the object as well. Okay? But now we're interested in what actually is the emergent. That is that the radiation escaping from the atmosphere, for example, in the direction to us. Yeah? That's what we will observe in the absence of these type of interstellar or intergalactic extinctions that we talked about last time. So, all right. We put this in, then I nu of 0 mu. Then we can see that, well, the first here term is actually going to be 0 because this one is 0, but this one is goes to infinity in the semi-infinite case. So we're not going to get any contribution from here. So the only thing that we're going to get is this one over there. Yeah? And we have said that this one is 0. So we're going to see this from 0 to infinity as nu of t nu e to the minus t nu divided by mu d t nu. Oh, pardon for that. Okay. So now we have a neat equation for the light that emerges from this plane parallel semi-infinite atmosphere. I'm going to write it again up here. We can take away the stuff over here. Right. So what did we want to do with this now? Well, that's a good question. Let's look at some examples, okay? First, like we had before, let's assume now that S nu of T nu is actually just S nu, a constant. Okay? Right? Well, then this is not such a difficult integral, hopefully. We could do a variable substitution and show it with x, T nu minus mu, etc., etc. We evaluate this, then I nu of 0, mu, is just going to be the source function, right? And that we could have that we should have known already, because that was the result we obtained from the homogeneous slab in an optically thick media, right? So the homogeneous slab would be the mu equals to 1 case here, and in this case, tau nu would be much, much greater than 1. And then we get that the specific density is just the source function, right? So that checks out. Very nice. Now, you can do this as a little exercise for yourself to verify that if you have this and it is this, then the flux in the c direction should be pi times the source function. Yeah? You can verify that, get you working with the expressions for the flux, right? And then you compare that to when we had that, okay, before we had started to do the radiative transfer, we had that the flux from this type is like pi times I nu. In the case that we had no incoming radiation and the radiation field was independent. That's a little bit of a next exercise for you. Now, we're going to do another example, because the drawback with the homogeneous slab is, of course, that, well, a lot of objects aren't really homogeneous in that sense, right? The source function do vary with position. So we're going to assume now that it varies as a function of optical depth. And it varies linearly as with the optical depth. It increases with the optical depth, which for our semi-infinite atmosphere means that the source function increases as we move into the material. Okay? Again, a star is the natural example to think about here. Because we know from our other courses that the temperature increases inward, so we can think, well, the source is roughly the Planck function, and so the Planck function should be bigger and bigger and stuff like that, okay? One can do this more quantitatively, but that's a qualitative way to think about it in this way. So if we assume that now, and we plug that into this, we get I nu 0 mu equals 0 to infinity A nu plus B nu T nu, yeah? It's the source now, using the dumb integration variable, dt nu mu. Okay, so the first term here, we recognize, that's just the same as we had before, the constant term. There's a mu here, there's a mu there, and there is a nu there. Oh my God. Terrible. So the first is just going to be A nu. That's the same exercise as we did before. That's the constant. But now, of course, we have this. So in this case here, we need to solve an integral of this sort, B nu x, integral 0 to infinity. No, not x. Oh my God. Mu x e to the minus x dx, where I've used x equals to t nu divided by mu. Okay. Did my on-the-fly variable substitute and pan out there? I think so. I hope so. You can check me and you tell me if I'm wrong. Yes, please. But you have the x, it's the t nu, right? Mu. Yeah, but you have this one. It cancels out there. But then you have this t nu. So t nu here, you have to have x times mu. So this is the mu that comes out from that. Yeah? Yeah. Now, this integral, you can solve, or nowadays you can, talk to your favorite AI assistant and get some assistant. It's not that. You solve it by integration by parts. Then it's actually straightforward. That's not what we're going to do today. It's not really the relevant part of this. The relevant part is that it comes out as unity, which is neat. Okay? So that the answer here is A nu plus B nu mu. Okay? Okay, that's interesting. What do we recognize by this? Well, it has the same form as the source function that we assumed. So we can write this as S nu tau nu in the c direction equals to mu. Okay, so what have we done now? I knew of mu equals 2 S nu tau nu surface mu. This is called the Eddington-Barbier approximation, and it's extremely useful in understanding some basic properties of radiative transfer. For example, we had a semi-infinite media now. We see to some sort of certain distance. We know that it's going to be so opaque such that we don't see stuff from the most opaque layers. Now, what is it that we actually see? Well, we see the source function, but now that varies with optical depth, so with depth in the object. And where do we see it? Well, if we sit here now, yeah, and we're viewing this, and John, right? So mu equals to 1, we can call this one. Mu equals to 1, yeah? Then we see that if this is the surface now I'm going back to our plane parallel approximation. So this is the spherical version of it, right? We see the source, as it were, in this case for mu equal to 1, reflected at tau nu in the r direction here of 1. Right? So say that that's there. Then we see the source as it were at an optical depth of unity. And that's, of course, why we talk about this transition of optical depth unity as the sort of characteristic layer from which we see the light emerge. Right? Now, let's look at some position closer to the limb. Yeah? We're very, very far away here. Huh? So we see only parallel rays. So we're going to see this, and it's almost at mu 0. Huh? Now then we see the source function at, in the radial direction, a higher position. Say we have mu equals to 0.1, then we only go down 0.1 in optical depth along this direction, so perhaps here. Yeah? Now, remember that this was defined along the fixed coordinate. But if you were to now say along the c coordinate or the r coordinate equivalently, then of course we know that the tau nu along the ray, yeah, is just going to be tau nu theta divided by mu. So if we take this in a plane parallel atmosphere, what it means is that if we're watching here, we're seeing down along the ray to tau nu equals to 1, right? And for a ray along the vertical in this case, that's equivalent to the tau nu c scale. Now, if we position ourselves here instead, and we're watching like this, we're still gonna see tau nu along the ray unity, but that is going to be reached earlier in the atmosphere in terms of the vertical scale. This instead of here. And then we're seeing an upper layer. Okay? So it's along the ray that we're always seeing to optical depth unity, but the distance in the atmosphere in the vertical direction is less. And what does this mean? Well, we're going to see the source function reflected at those layers, roughly. So here, this is going to be the source function that we're seeing from this, but if we're positioned here, we're going to see it from this layer, which is deeper. Now, if the source function increases downwards in the atmosphere, which we have assumed, then of course this one is going to be higher than this one. So we're going to see more intensity at the center, mu equals to 1, than at the limb, mu equals to 0. This is going to be higher than this. And this is then the basic explanation for limb darkening. Okay? Now, let's see what time we have. All right, we do have some time. And like I said, such limb darkening can be important in various contexts. If you look online, you will see limb darkening of the sun. Very easy. I already mentioned, and we can just sketch this out. For example, if you have now a star emitting here, and you want to analyze a little planet going around this star when it comes in transit here, right? Then you look at the light curve, and you see that if there were no limb darkening of a star, then of course the light curve will be something like this, right? Yeah? But if it's limb darkening, then of course we're going to have more dips when it's in the center than when it's here. So that's one way where it's actually, if you want to have precise parameters, you need to account for limb darkening in that sense. Just as one astrophysical example of this. Now, you can also think of instances where this is opposite. That is, the source function decreases when we go inwards. That is, that it increases when we go outwards in the atmosphere, right? And that's, for example, the case in the solar corona, where the surrounding corona of the sun is very, very hot, for reasons which we will not discuss in this particular course. And there the source function then can actually increase with height, and then it leads to the reverse phenomena, which we, of course, would call not limb darkening, but limb brightening, indeed. Supernova can also be exposed to such limb brightening effects. That's just two examples of that. And then the basic thing is that the source function then increases outwards. Yeah? We will come to, hopefully, get an intuitive way, feeling for when it is increasing inwards and outwards in various astrophysical systems. All right. Now, we also now see why we associate kind of like optical depth unity with how far down we see in the medium. One final thing here then that we're going to do, what about the flux? Okay, so we can look at this expression now and see what does this mean for the flux emerging from the object in the z direction. Well, we only have variations in the mu, so we can directly write down this integral here, where the phi angle, of course, has already come out. And then we had the I nu of 0 mu. And then we had mu, the mu. This was our expression for the flux. Go back to those lectures if you do not remember it. Now we can just plug this in our Eddington-Barbier here. Where is it? Did I? It must be somewhere. I've sort of cancelled it. So the original expression was, of course, A nu plus B nu mu. Yeah, very pedagogic. So, and that was then our I nu of 0 mu. So we had nu plus B nu mu mu the mu. Okay, so what do we get out here? Well, the first thing to realize, this is only in the upward directions, yeah? So the flux integral then, of course, goes only from 0 to 1. Remember the discussions when we first introduced the flux, when we later introduced the effective temperature, the emitting surface where no incoming radiation. So then we get something like 2 pi. The first integral is mu from 0 to 1, so a nu is just going to come out, and that's just going to give you something like a half, right? A nu divided by 2. The second there is going to be the integral of mu squared 0 to 1. That just gives you a third. So it's this one there. We can just plug this out, and then we get, we take out the 2, then we get pi a nu plus b nu 2/3. So what is this? Well, this is pi. Then the source function at an optical depth c equals to 2/3. So we see that the intensity is always merging from along the ray an optical depth of unity, right? You take that, you put it over all angles, the average then becomes the flux. The weighted average becomes the flux, and that's then a reflection of the optical depth along the vertical axis of 2/3. And that's the simplest way we can think about why we often, so to say, define the surface of the star, the photosphere of the star or the object, the accretion disk or whatever it is, as the optical depth of 2/3. We will next week also look at a simple, very simple gray atmosphere model where this also comes out to be at the optical depth of 2/3 to further solidify that. But that was it for today, I think. So I call this the summing principles. Yeah. So of course, what you can have in a real situation is that not only at a given frequency, not only one process contributes, but several. So what do you do then? Well, then actually, if you have several at the given frequency nu, then you can just sum up over all contributing processes at that, the extinction coefficients. So if you have processes I that contributes, then you just sum up all contributing processes I, you just sum them up. Similarly, for the total emission, you just sum over all individually contributing processes I. Okay? So they are just linear combinations. Right? But then you can immediately see that for the total source function, that is not just summing up over all individual source functions. How do we see this? Well, imagine we have somewhere in the spectra where we have both a continuum and a line that contributes. That's a standard situation. Then you can see that the total extinction will be then line, I call it, plus continuum C. Yeah? The total emission will be line plus continuum. But of course, per definition, the total source function is the total emission divided by the total absorption. So in this case, this is alpha nu line plus alpha nu continuum, eta nu line plus eta nu continuum. And this is thus not equal to S nu line plus S nu continuum. This you can very easily verify yourself. And this is important because actually what you can show, and this is then another background exercise for you to carry out here, is that if you have a line and a continuum component like this, right? Yeah? And you can assume equilibrium in both, then we already know that line source function is Planck. Also, the continuum source function for such a thermal process, as we call it, will be Planck. Yeah? But then you see that the alpha nu total will be the sum, right? But the S nu total will just still be the Planck function if you can assume equilibrium conditions. It will actually not be 2 times that, which would be the sum, right? Yes? I switched them around. Yeah. Either, thank you. Yeah, otherwise I would have violated the definition of the source function. That's not so good. Thanks. All right. Now, here I wanted to mention one thing which we can actually now gain some further insights in, and that is the general problem of astrophysical radiative transfer. Problem of scattering, we may call it. What do I mean by this? Well, for a scattering process, then we don't have any transfer of the energy between the thermal pool and the radiation field. So what do I mean by this? Remember that we discussed different processes, right? We had a photon coming in, and now we know what's actually happening. The photon might get absorbed by, say, the hydrogen atom, right? And then the hydrogen atom goes up to the excited state. Yeah? So the hydrogen atom has increased its energy, but we have lost energy here. So what does that mean? Well, we're losing energy in the radiation field. We're gaining energy in what we may call the thermal pool. That is the atom, right? Then this might come back, and then the reverse happening, okay? But if we have scattering, say we have an electron here, and the photon comes in, and then instead of being absorbed, it's just scattered out of the direction. Then we know, since we're computing it along some ray, that it vanishes from the ray, right? Just goes into another ray, though. So that's a redistribution, okay? So that's scattering, but we can see there is no transfer of energy between the radiation field and the thermal pool for such scattering processes, right? So that's fundamentally different then. And then what you can do is that, okay, we know then that the emission from such scattering, let's call it sets, over all solid angles, that is in all angular directions here, must then equal the extinction for scattering times the specific intensity at that point, okay, over all angles. That's just the conservation of energy. We even saw it when we set up the radiation energy equation, remember in chapter 3, yeah? And this is just then a statement of that the right-hand side of that energy equation under those conditions is 0. So if we now assume that this and this is isotropic. Okay? Then we can see directly that for this scattering, alpha nu scattering times J nu, where J nu now is the mean intensity. Remember how we define the mean intensity? 1 over 4 pi I nu d omega. Yeah? So here you can see that the source function for a scattering component is just the mean intensity, which is not necessarily the same as the Planck function, right? Only in a complete perfect thermal equilibrium are they the same. So why does this pose an issue for us? Actually, it poses a very big issue for us when it comes to developing astrophysical models for interpreting spectra. And the reason is the following. Now, if you have now an alpha nu total that is composed by one thermal process, we call it, plus one scattering component, okay? And similarly then eta and stuff, yeah? Now then, again, this is an exercise to show, it's just a little bit of algebra. You can write the total source function now as a parameter called epsilon often times b nu, which is the Planck function of temperature, plus then 1 minus epsilon nu and j nu, where your epsilon nu is your alpha nu thermal divided by your alpha nu thermal plus your alpha nu scattering. So what does this mean? Well, it means that if you have only thermal processes, that is, if your alpha nu scattering is 0, only thermal, then you see that epsilon nu is 1 and your total source function is the Planck function, yeah? On the other hand, if your thermal component is 0, then you see that your epsilon is 0, so your total source function is just the mean intensity. So epsilon equals to 0 is a pure scattering situation. We have only scattering processes contributing. Vice versa, epsilon equals to 1 is a pure thermal process. We only have this type, you know, depending on what we're considering, and the source function is always the Planck function. In general, we have a linear combination between the both, so that epsilon is interpreted as a photon destruction probability often, which you can see why it's interpreted in this way from this. It's the probability for when you have your interaction, do you destroy the photon, you leave the energy to the thermal pool or not? All right, but let's now consider what's happening here then. We go back to our chapter 3 in the course book and our radiative transfer equation along a ray, which we know we can formulate in the following way. Yeah? Now, first, let's assume thermal. Okay? Well, then we have the I nu, the tau nu equals b nu, Planck function, I nu. Okay. But the Planck function only depends on the temperature. And for example, we already saw that, okay, if we have some background light illuminating something with a constant temperature, then we're interested. we already know that the emergent intensity then in this, we can just write down the solution, right? For such a constant temperature slab, it's just B of T 1 minus e to the minus tau nu, where tau nu is the total optical depth of the slab. This we have seen. Remember, even in the situation where we had like an atmosphere or something, T varied, right? But then we could still solve the equation. We just had like an integral that we needed to solve there. And if we know the temperature distribution, we could still solve it. The Eddington-Barbier, if you remember, the limb darkening was derived by this equation, assuming that you had a source function that depended linearly on optical depth in temperature. Yeah? Now, look at what happens. Let's assume we have the extreme situation, pure scattering. Yeah? Which equation do we have to solve? J nu minus I nu. If we write this equation out, we see the issue. That is the surface integral over all omega of I nu, the omega minus I nu. So what does this mean? Well, what was the transfer equation? Well, it was the solution along a given ray, right, in some specified direction. Yeah? So, and then we were interested in the variation of I nu along that ray. So if we want to solve that, though, for a scattering source function, what do we need to know? We need to know the value of I nu, but not just in that direction, in all directions. In that direction, 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 in that direction. Because only then can we get the mean intensity that we need in order to evaluate this in the first place. So it becomes a highly coupled problem, where in order to know the specific intensity along one ray, you need to know the specific intensity along all rays. Yes? Sorry? Yes, I forgot the 1 over 4 pi, thank you very much, in the definition, yeah? Scaling. So this is typically in mathematical analysis called an integral differential equation. It's much, much, much harder to solve than this problem. Yeah? It's a very interesting problem, though, to solve from Barry. And it's often solved by numerical iteration techniques. Yeah? A few of them, if you, this goes way beyond the scope of this introduction course. I just wanted to now let you know of the basic issue that we're facing here and what in practice often needs to be done so that you can have a proper understanding of what the difference between scattering and thermal processes. For example, in the master's course in stellar atmospheres and wind, we will look at specific numerical techniques for solving this type of equation where you have a scattering component. Yeah. It's iterative techniques where you typically start. The basic idea is the following. You start from some guess of J nu, right? Say the Planck function. And then you calculate this along a bunch of different rays. From those different rays, you get an estimate of J nu. Then in that iteration, you insert the new value of J nu there. Yeah? And then you can solve it again along a bunch of different rays for the new updated that, and you can form your new J nu, and then you try to iterate toward convergence, essentially. All right. So that is how we have now connected a lot of what we have discussed back to our radiative transfer knowledge, actually, I just realized that one of the applications which I do in the chapter 8, 2 or 3, which has to do with the line profile function. So you can see a line profile function there of different depths. That assumes a thermal source function. One could actually do an extension of that to a scattering source function to illustrate the different. That could actually be included already here. Something for me to think about. Anyway,